Welcome to the companion video for the controllers lecture for robotics, with the simulator being our focus. So this task here is first to show you how to start using the Arduino in the simulator. Now again, be clear that using it in the simulator, there's a lot of stuff that's the same for wiring and hooking stuff up and doing some of the coding, but there's other aspects that you don't see unless you are working with the physical equipment. So again, please watch every week the actual physical equipment video that comes after this. So to begin with, again, you want to go to Tinkercad and make sure that you're under circuits, and you can create a new one if you want to play around or follow along. This video will show you the basics of how to use the Arduino in the simulator and start some of the understanding of what's the syntax? What's the language? How do I start getting a program going? We won't do a ton today because I want to do future lectures on starting to get into different effectors and actuators, which will then start bringing in some of the other syntax and things we can do. And then once we've practiced with some of those, anything more advanced, moving on to a little bit more advanced robotics things. So as usual, the simulator works the same as before, that you have your start simulator, you have your space that you can work in, you have the components that you can drag and drop, and right now they're just under basic. You can see that at the top right. You can always search for everything. So even in here, you can see some of the stuff we were working with before, the battery sources, but now you can see that we have an Arduino Uno. Before doing more with that, I just want to quickly mention there's one here called a microbit. This is another microcontroller that's out there that's designed more for, again, introduction with kids. It has a lot of sensors and stuff built in, but has similar things that it provides, like the pins at the bottom and voltage and ground and stuff that you can play around with. Boom. Now, there's way more in here. Always realize there's other stuff that you can start playing around with, like just going beyond the basic components. You have advanced for extra things that are within here that we'll try playing with as we can in the course. Extra lights and fancy things like that. You also have cases for already done Arduino setups. So you can see one here that is with a breadboard already connecting the power, and a few other quick examples that don't use breadboards but show some code examples of how to work with some of the things that could be similar tutorials from the FreeNova kit. But for us, I want to go back and go from the very, very basics of doing work with it. I'll just click the basic, and you just want to, just like before working with the breadboard and anything else, we want to drag over and start using our Arduino Uno. You can see even here is that while we're not in the simulation, it's doing the step that I said if we're doing any wiring, you have it unplugged, so it's even showing us that it's doing that. And then you have all of our connectors, here your pins, your GPIO pins, your power, and so forth from there to work with. If I zoom out. So if we start doing a simulation right now, not much is going to happen. You're going to see that this one little light here is glowing. And the idea is here is, like I mentioned before, like with the microcontroller, it has one program loaded on it that always continuously runs. And if this is the first time you're ever turning on an Arduino and it's never been used for anything else before, they always have a default program on it that basically makes a light blink that's on pin 13. Now what's weird about this is they just have this kind of little test LED that basically is connected to pin 13, so they can write code and it's going to verify that the machine is working properly and just do stuff. So this is the program that's loaded on here for right now, and we'll keep running on here until we upload some new code. So again, you want to click Stop Simulation. And the way that you can start coding anything is, again, you can see up in the top right here, is you have the little code tab that will pop out. And it's going to pop out where you'll do most of your coding in the simulator. Now, by default, it's showing you here a blocky style way of coding. So you drag and drop the little blocks to do more work. And you can see an example of the program that's loaded on there already for blinking a light. But I really don't want people working in this. If you're in the comp course in the BCS, even if you're coming from the science courses, it's best that you try playing around with the actual direct code. Now, to change it in the very beginning, and this happened generally, I think, every time you drag an Arduino, it defaults to blocks. you want to go to the top and switch it to say that you want to do text. And just say, are you sure? Continue because you can't go back. And then boom, we are right into the direct C style kind of language for the Arduino. And you can see that we have our setup function and our loop function already in place. So now what I'm going to do is I'm just going to delete that. So we're starting from blank. You can leave it there and modify it. I just want to start directly from blank and then explain a few more things about the language. So one is that when you're starting the program, at the top, some of them, you may see things like this, whereas a slash star, a star slash. And remember this, if you've done this in Java, anyone from here, you'll recognize this, that this is block commenting. For people coming from Python, this just means that everything between the slash star down to a star slash is commented out, so it's not treated like code, and you can type what you want. Boom. So you can have these throughout. You also have your general like double slash commenting. That is good for just a single line of commenting. And it's good to have anything extra to explain your entire program. After that, for every Arduino program, you always have to have two functions defined. So it's always saying void setup, open and closing round bracket, and then your curly brackets, and then void loop. Now, I'll explain this again for breaking this down, is that for even people in Python, you should recognize that this looks like your function definition, so not the call of it yet, but you're setting up the actual function. Always having a name, your open and closing round brackets where you would put parameters, and so forth. So you have to define them like this. So you have to have void, setup, all syntax and everything should be right, should be highlighted, upper and lowercase is important. It should all be in lowercase for right here. Now, for people who are coming from Python, when you're dealing with this language, normally in Python, you would just have the function name and then your parameters, and there's nothing that comes here before. And you would have where you could return. Now, in C or Java or C++, when you're defining functions, you have to say, well, what is the type of the data that the function's going to actually return? And that's always defined here before. And so these are data types that you're working with. And so you could see things like int, you could see things like float, double, and more like these. And you can look up more types like this, and you can see that it's recognized them as keywords because it's kind of purple. So you have int for integer, so 1, 2, 3, 4. With no decimal places. You have float and double, both are basically right now, as far as you're concerned, can be treated that they're dealing with floating point numbers, meaning any number that has a decimal place. So 1.2, 2.3, 3.4, and on like that. And the difference here for double, it just means that it can hold a larger number with more decimal places that's in it. So these are going to be for your variables, your return types, everything. You must have those for functions that you're defining, parameters, variable, everything. Now, when you have the word void here, what it means is that the function returns nothing. So for return types, if you have void, does nothing. So for both of these, okay, these are your functions that you're setting up. They don't have any parameters that are defined in here. And now afterwards, you have to have at least an opening and closing curly bracket, and you can have any number of spacing. For Python people, you don't have to tab in anything anymore to say indentation. There's none of that. How you indicate that code is inside of that function definition is you have it between the opening and closing curly brackets. So these can be anywhere. They can be before, they can be after. You can see different combinations like this, and this is purely legal to do syntactically. For stuff. I just like to keep them down below to keep it easier to read, and then putting some spaces in just purely for readability. Okay, so these are our two functions. Now, the idea is that this program here does nothing. I'm just going to remove the commenting, don't need anything else there. Now, this program does nothing if it's loaded on. So nothing's running yet, but it just means that, well, there's nothing in the functions for the setup, there's nothing in the function for the loop. And when the controller starts up for the first time, so saying that we've clicked Start Simulation and the Arduino's given power and it's running, the first thing that happens is that the setup function is actually called and any code that's in there is executed. So this is always things like specifying what your GPIO pins will be, what your variables are, like what they're set to for initializing, and any kind of setup features that you need. Once this is done running, nothing else will happen until this is done running. So you want some just quick actions in here. Then it automatically goes and it calls the void loop for you, and then any code that's in here gets continuously run again and again and again and again. So whatever you see in here goes to the bottom and loops back up. And this is again going to be key for when we want to take advantage of that robot control loop. We're doing a closed loop, is this having continuously repeat and do work for us. So we don't want to treat it like the main where you go from the first line of code to the bottom and then the program stops. You have to think of it about being, okay, what actions are we having repeatedly done the entire time the actual robot or the controller is running? And how take advantage of when we reach the bottom, what happens when we get to the actual top. So I can test to see if everything's working. There's no separate compilation. If we hit Start Simulation, it's going to automatically start running the actual simulation. Now in this case, you can see nothing's happening. We got power going into the Arduino, nothing's lighting, and you can see, well, that light's off. Well, that's because we now just overwrote that previous program, that it compiled this, loaded it onto the actual chip, and now that this has power, it just continuously keeps running this program that was here. And so now it's not changing the light. We're not doing anything else. So we need to start adding some stuff in. Next, we need to worry about, okay, well, what if I do have an error in my code? How am I going to see this? And it's going to be very blatant in the actual simulator. It doesn't mean that the error message you get will always be as informative, but you'll know you'll have to fix something. So, for example, I'm going to take out the brackets as if you were doing stuff in Python and you just forgot that you need to have brackets instead of tabbing, and leave it here and go start the simulator, and boom. Gives us a highlighted red line, and now here down at the bottom, if it's giving us our output saying, well, what's wrong? Like here, expected initializer before void, and it's saying, oh, here, line 10, character 1, and you can see it's already highlighted it. So it's saying it's error here, but the idea is, well, okay, we have this function, but we don't have an opening and closing curly brackets. So again, not as informative, but it's first indicator of saying, well, okay, how do you have an error in your program? So if we go Start Simulator again, okay, boom. There's nothing wrong at all here. Okay. Next, I'll start talking about basic variables. So there's two sections and areas where you can define variables, and it depends upon how they're being used and where they're being kept. So one, if you're doing temporary work where it's a small variable, you're just using it for a little bit and you don't care about the information that's kept in it long term, you'll define those inside the actual functions, say like setup or in loop. Right here. So declaring a variable, usually have things here. Let's say we do a very simple one like int x equals 0. Now, everyone in Java, this is the same. So everything that you remember from Java, if you're doing C++, all your declaration of the variables, everything you've learned from there is exactly the same here for your basic primitive types. You won't have anything for objects or anything else like that, like the string class, if you're trying to do strings and stuff. That does not exist here. You have to do it in a different way. But for your basic ints and floats and booleans and stuff, you've got that case. For people who are coming from Python, once again here, normally you would have, if you're declaring a variable, would have tabbed it in and you would have just said x equals 0. And this now means it would have created a variable and assigned it the value 0 and made it an integer. Well, in this case, because we wanted to store integers, we have to declare the type. So just like we had for the return types, you have that int, float, double, and there's others. You can look up the primitive types in the language reference. And we go int x. And we could just define it like this and be done. And what you have here is this case of being the semicolon now is your indicator of end of line. Instead of where in Python where you'd normally hit enter and then tab in, you would just have the semicolon to say, okay, this is the end of line. So for people who are in Python, this is going to be the biggest error you're going to have in the beginning because you're so used to just hitting enter, not thinking about the semicolon at the end of a line and where to place them properly to indicate that. So be careful about that and try looking at some other example programs as you're doing work. The other case I started with equals zeros, just initializing it in the very beginning, which is always a good idea with variables. So we have that int x. Now, the idea again with these variables is defined inside the loop, so it's only good as far as it's defined here. Like every time we go in this loop and it's being executed, these variables be recreated. Unless there's some weird case in loop and it keeps that information continuously for you. So you just want to treat these as local variables that you're only temporarily using, and you define them within here. Now, if instead you realize, hey, wait a minute, this is a very important piece of information that you want to keep for like the lifetime of the program and modify as you go, well, instead what you do is you declare what's called a global variable when you're working here. So you define it outside like this, and this is still legal to do right now. So what this means though is once the setup function's done running, or the loop function's done running one iteration before it goes back to the top to repeat, these variables will not be wiped away. They will exist for the entire time of the actual program and whatever values were in there beforehand. So this could be, and you want to use some a little bit better name, things like maybe like state or something like light level, like that, as an indicator of, okay, like maybe we're keeping track and dimming and glowing, like dimming and brightening an actual light, and we want to know what light level we have it set to, and we want to keep that continuously and doing readings. And so we'll declare the variable up top. So again, good practice, and I'll be looking for this when I mark, is if you're using variables that are only locally used for a little thing like reading a value from a function and moving it to somewhere else and never cared about again, then they should be defined inside your actual functions as local. But if it's something that's more important for memory that the actual robot or controller has to keep track of the entire time it's running, then you want to have this up here. And remember again, for anything that's your variables, as soon as we lose power, that information is gone. So once you start it back up, you can't expect that information to be there. You got to write that to that onboard EEPROM memory, which don't worry about how to do that now. That'll be future in the actual course. Okay, so these are the basics. They'll take practice, and especially for people Python, I say go through some tutorials, work through some examples, and come back. Now, we should probably start trying to get the actual, like, Arduino to do something slightly useful and then build up a little bit extra knowledge for some of the extra functions and features of how to actually use the Arduino itself. So we're going to go back to what I did in the electronics notes where we were just hooking up a light and getting it to some power and getting it to turn on. Now I'm going to do this in two different ways. One where we're just going to use the Arduino to get power and not use any of the actual GPIO pins to do work for us. So just kind of recreating what we had from that first circuit, but we had hooked it up to a 9-volt battery to get the power. But instead now we're going to use the pins that the Arduino offers to provide us power and just get it to go on. And next, then we're going to change it so instead we can take that same circuit, hook it to a pin, and then use that pin as a way to control what happens to that actual light. Basically making an on-off switch and doing different work. So first things first, we need to set up our actual board. I'm going to zoom out a little bit. And now you could bring in the components right here and start drawing the wires, but I'm just going to bring in the breadboard just so we get used to using that as we start building the rest of our actual circuits. Now, the first thing that we want to do to give good practice is hooking up these lines just for proper use. You can modify and use things as you see fit, but just for right now, I want to bring those over. Now, what we want to zoom in on for the Arduino is we have to find then the pin that provides us power, and they make that kind of easy because they have it labeled as power over here, that these pins are in relation to power, some more advanced than being others. And we have other things here. And we want to remember for a circuit that the positive is, again, is where we're getting power from, and then we want to go to the negative. And on these boards, G and D will means ground, which represents the negative. And what you want to look for is where it says V for volts, is that these are two of the pins that are providing power. Now, when it comes to these pins, you're not shoving multiple wires into these. Remember, it's only going to end up being one jumper wire that you're going to use now. And so when you have this 5 volt, you can take this out and then share it along a line, like we can share it in the breadboard or everything else, and connect everything together that way if we need to have multiple circuits connected to the same board. So this is Arduino. We have our 5 volt right here, and so I just want to click on that, and then I want to start dragging it over to the actual Arduino. Oh, I'm just going to be picky. I've got there. Now I'm going to delete that. I am just being my own OCD, and I'm just going to go from here, go down, just so it looks like a cleaner actual line. Not very important. Now here it's left as green, but again, good practice, and I'll start checking for this in the actual future as part of the marking, is I'm just going to mark it as red. Red doesn't mean it like is power all the time, it just makes it a lot easier to follow and change the wires that you're actually using. So here we've hooked up the 5 volts. We can see this is still unplugged. Next we want to hook up the actual ground, and we have a choice of 1, 2, or 3. All of them do the same thing. These two here are for something different in the future for getting power into the machine, so voltage in and ground in. But you can still use it right now as your negative pole. So it really doesn't matter which one you actually use for right now. So I am just going to pull it over from the same one, just next to our VIN, just because to keep this somewhat consistent. Put up and then over. And keep this one to black. So what we've done there now is that we have our ground going up and we have our power. And so in this case, remember, these are not pins that we can control. They'll just be that when the Arduino gets power, 5 volts comes out here, and then the ground is along this line. So now we know we have ground all along here, and we have 5 volts all along here that we can pull along. Next, we want to pull in a LED and a resistor. And remember, the resistor's there just so that we don't have too high of amps, which just being careful with the Arduino. I don't remember off the top of the hand the amount of amps that are coming out of it, but you can always look that up in the specifications. But we just want to put a general LED resistor and get the LED and get it all hooked up. Okay. So pull out a resistor, and here it's saying 1K ohm. Should be fine. We'll see if it blows up. This is the simulator. We just need one that's giving at least some resistance because we're not working with any too high of power sources at this time. And so remember that this can be on the anode or the cathode of the LED, so the plus or negative. I'll then pull over an LED as well. This time, just for fun, we will make it orange. It's off. And you remember right here is that looking here, you have the cathode, meaning that's where the negative has to be attached to, and you have the anode, that's where the positive has to be attached to. Because again, this is a diode, which only allows current to flow through it one way, going from the anode to the actual cathode itself. If you hook it up the opposite way of positive here, negative here, this light will not turn on. So we'll go and get this into the board. And then once again here, boom. I am putting it in between 2 rows because then it means the anode is connected to this entire row right here and the cathode is connected to this entire row here. So next part from this is then to bring in the actual resistor and connect that. I don't want it connecting to both rows, so I want to click on it and then at least rotate the component so that it's going across rows. And this time, instead of using wires to connect everything, because we have the leads on each side, I'm just going to save space, and I'm just going to have one side of the resistor on the same side as the anode, and another one in a different row that it fits into. Now, this is perfect okay. Remember, with resistors, it doesn't matter what direction you put it in. It'll still be perfectly fine. It's only for anything that's a diode as far as you're concerned right now. So far for our circuit, we'd have something coming in here, going up to here. I'm going to even move this down just to show that it doesn't have to be right next to it. But we go here, going through the resistor, which is going to slow down the whole flow of the current through the entire circuit. And then it's going to go from here up to the anode, through the LED to emit light, and then right here. So we still have an open circuit, so we need to complete everything else. So from here, we need to have, again, the cathode needs to go to negative. So I'll just draw a line, get it down to here, and I'll change that to black. Just to still say that, make it easier that it's still following from here being negative. And then next here is anywhere on this row, we need to connect the positive, because again, this is going up and through the anode. So here, down to the actual positive, and again, just being red, just to make it clear that when I'm pulling stuff from the rail right here that has the negative, ground, it's going up, and here's the positive. So if we check everything from being our circuit from a cycle, that we're going from our positive all the way up, going down here, up and then through the resistor, then up here through the anode, through the LED, down to the negative, down to this rail, and then back to our battery source, and we should have a complete circuit. So it's not open, should be no shorts, and right now this is just the power. So again, the Arduino's not being used really to control anything in the code, nothing in the code will actually affect at all. It's purely just using the power outputs from the Arduino to run the circuit we liked before. So we're treating the Arduino right now basically like a power source. So as soon as we click Start Simulation, this will get power, and we should just see the LED turn on. Okay, there we go. You can see that we got our LED turning on and everything's okay. So basically, again, we've recreated what we did in that first circuit now, but just using the power output pins that are provided by the Arduino itself. So I'm going to stop this. So the next step for this is we just want to get the Arduino to start doing something, and we're just going to start getting it to do a basic blink kind of thing. Now on this case, when you start learning this more, and we'll do it more next week with actuators, is that blinking is basically like, if we're trying to control this, that just means like, well, we want power to go to it, which means the LED's on, and if we cut the power to it all, creating an open circuit, the LED will shut off and be off. And if we do that properly, we should get some kind of blink at a specific rate that we can play around with. Now, if you're doing this at home, you're used to it. Go to a light switch, you're turning it on and off, on and off, on and off. And when you get on and off, this is the idea of a digital signal that we'll talk about more, most likely next week. And so for these, you want to start by using the pins that are over here for the digital pins. Now, some of these are marked where you see TX, RX. You get things that have the tilde and stuff like that. And right now, we don't have to worry about this too much. I would stay away from using the pins 1 and 0 for right now and just go from 2 to 13. And we'll learn later what this little tilde means. But for you, as far as you're concerned, we can pick any one of these pins. And so it just means right now, as we're wiring stuff up, I want to pick one of them being digital. And I know in the future, I'm going to plan, okay, I want to use this so I can control it as an output. So being an effector or an actuator, in this case, will just be a basic effector, and I want to use that to control the actual circuit. Now, the important thing for this is that this is going to be basically like providing power if we're doing anything else. Before, we were using this line to provide our power and do the rest of the actual circuit, so it would flow through it. This instead is, well, with these pins, basically, like, you can read signals coming in if you're getting 0s and 1s, kind of power, no power at different levels. But we're going to use this for output. So this means, well, we want to, through that pin, we can control to say, hey, that pin has no power, so it's 0, or it has full power, which is basically that 5 volts that we're working with. And so we can control that. So in the code, we can tell the controller, hey, on that pin, put no power, or put more power, and so forth. So what we want to begin with is, well, we don't need, boom, these power here. We're not using anything for the power from the Arduino. That could be used for other things if it needs, say, motors or other stuff, basic motors. And we can leave the ground because we still want to have that circuit, because this is going to provide the power, so that's going to become your kind of power source for the circuit, this one circuit we're hooking up. But otherwise, we'd still want the actual ground hooked up, because this is the ground that's coming back to the Arduino to complete that actual circuit. So instead, we want to hook here where we had power before over to whatever pin we choose. So arbitrarily, for no real reason, I am going to choose the pin 8 and bring this over. And now I'm not going to put it to the power rail. I'm just going to put it to the line where I want it to actually connect. So up here, to the actual resistor. So we can see that we have here going down. This line is green. I'm just going to arbitrarily change this to orange just so I have a wire that I can control. If we have more and more, we can change these colors to make it easy to read. So what we have here now as a circuit is that, well, pin 8 will be our power source, where in code we can control to be on and off. And so from here, it'll flow through here for the power when we turn it on, up through the resistor, everything else here, and then back down to the ground, and that becomes your power source. But the difference here is this always provides power. This is then in your code. You can then control to do what you want. So we've got everything wired up, so now we need to go and start coding everything. We need to remember that we've decided to use pin 8 in this case. We have to tell the controller for that GPIO pin that we are using it for actual outputting information versus inputting. There's default settings you can take advantage of in the future, but for right now, it'd be good just to, when you're whatever pins you're using, you set it to and you get used to that. Boom. So we'll go to the actual code and start doing that now, looking at what we have here. So and you always start with this setup, you have everything else. So the very first thing we need to do is we need to start defining the, okay, well, how is this pin used? And that is always done in the actual setup function. And this is the new function you're going to use to indicate this is called pin mode. So pin mode. So this is predefined. You can look this up on the Arduino webpage. You have pin mode and you have two actual parameters for this. And I'm doing this from memory. Make sure, okay, in Python people, there's your semicolon when calling functions. I'll do this from memory, and if it doesn't work, we will look this up on the actual Arduino IDE if I don't screw this up. So first thing, it should be the pin number you want to work with, which is 8. And then next is saying if it's supposed to be input or output. And this should be all in capitals, based upon my memory of it. So we want it to be for output for controlling, so we're telling, okay, pin mode. I'm telling Arduino, okay, pin 8, we want to use for output. Now, before I go on to anything else, I'm just going to click Start Simulation to make sure that I have nothing wrong in the code, and so far, we're good. No errors. If I had done something wrong here, I would have gotten some errors coming back to me. Okay. Well, next for us, sometimes having hard-coded values can be a pain in the butt, and a lot of examples out there will do this. And we can see that, so we've got this hard-coded 8, which is supposed to be the pin for the actual light, but this is not really descriptive. So right now, it'd be really good to go in and start defining some constants that you can use to represent what you're working with. And this would be really good, especially later on as things get more complex for your projects, that okay, well, you start naming your variables and the pin numbers and how they're being used to make your code easier to read. So one way to do that is const int LED pin 1 equals 8. So to do that, I'm defining a variable. Oops, that should be 1. I'm putting the word const in front of it to make this as a constant so that after I assign this, this value can't get changed. You can remove that if for some reason you want to change this, but for most pins, you shouldn't. I'm going int because I'm just working with a pin number. There's no decimal places, and I'm doing it all in caps, which is more semantics kind of thing. It's like convention. It's not a syntactical thing, but it's the skill that I've learned forever on is that if I'm declaring constants, I just put them all in capitals, just so that later on in a program, again, if you are seeing everything in all capitals, then it should be a constant. And it should be some descriptive name of what you're doing it for. So that's why I'm saying LED pin 1. So I know that this is being used for that first LED. You could take out the pin and just say LED 1, whatever you find that's descriptive. Okay, boom. And I'm putting it here so it's a lot more readable. And again, before going on, make sure that the code is working. Okay, so right now, all that we've got doing is saying we're telling the controller in the startup method that, boom, yes, we're going to use pin 8 as actual output. And then now when we come to the loop function, we can start doing stuff with that actual pin, which is basically just more like other function or calls. So another function you now learn about is that when doing outputs on a digital pin where you just care about either turning the power on and off, you use the digital write function. Boom. Put my semicolon. This one, again, similar to pin mode, has the first parameter is what pin you want to actually send the signal on. So using our constant, once again, makes it easier to read, easier to change pins and stuff around. And now next you want to indicate if you want it to be full power or no power. So right now, by default, when it comes on, there'll be no power. So if we want to have it go on, we'll just go, it's high. Equals. Just making a little comment here. So high, all in capitals, is a built-in constant that comes with the language that says, okay, that high means, okay, send full power, send the full 5 volts along that pin. The other constant you have is low, no power, which means no power. So it'll put it to 0 and there'll be no power going along those lines. So now I'm going to turn this on and explain what's going to happen in the code. Basically, what you're going to see is the LED is just going to turn on, but I'll explain what really is happening in here this continuous time. Okay, so we go running the simulation, and you can see LED is on. So again, when it's coming for the code, first time it's running the actual program, it's coming down here, setting that, making this global variable and a constant, setting it to 8, running the setup function, which then tells the controller to turn on pin 8 for output mode. And then we come into the loop function, and it's coming to this line of code, and it's continuously writing this line of code again and again and again and again. Now, the idea is you don't have to have a call again, because again, it's loop, it's running this, hitting the end, and going back up to the top, so it's running it again and again and again. Now, just to mention, and keep this in mind for future, is that with this function call, you don't have to keep calling it to have the lights stay on. The first time you make this call, you call it once, the light will stay on, and it's like telling, okay, you've told the controller that pin should be to high, and it's like flicking on the light in a room, and it'll constantly be high until you give it a different value. So by having this function here, it'll just keep running and running and running and running and running and running and telling it to keep setting it to high, even though you don't have to have that. So for example, if I take this out from here right now, okay. And this is where the online editor won't be the best. So I'm just going to comment this out. What's going on? Oh, in the simulation, what is my problem? Stop the simulation to change the actual code. So it's going to remove that out. I'm going to put it up here in the actual setup. Remove this, remove the comment for now. Is I'm going to do it in the setup, which is purely legal. Make sure I got that closing curly bracket. And so what this means in the setup is that it's going to call it once. The setup is going to exit. We're going to loop. There's nothing in here, but up here, we've already told the pin to be on high. So after this point in time, until we do another call to low, it'll just stay on. So we run it again, and you can see it here. So sometimes in your setup, if you want lights to be on at the very beginning of the startup of your actual project, you can do it up here. So we got digital right. So again, we've set it once, it's turned it high, told it in the controller, the program's moved on, the internal state of the controller is keeping the power going along here to actually be high, and boom. Okay, we'll stop the simulator. Now, that's not as interesting. It would be a lot nicer if we could get this to do something like actually blinking. Now, the normal thing you think to blink is we need to turn it off. So what we could do is, well, take this same line of code here and right after, and then just go low. So turn it off. I'm going to pre-warn you, there's a problem with this. Give you a second to think about what'll happen. And we'll just start running the simulation. And you're like, okay, well, it's dimmer. It doesn't seem as bright. It's kind of on, but it's hard to tell what's going on. We can stop this. So there's no light there. And this is where the simulator is not the best, is in the physical device, you see something differently. Now, what you have to realize is that it's running this line of code and this kind of code continuously. And these break into more instructions, but you have to remember this is running like thousands of instructions per second. And the human eye will be slower than what this device is actually doing. So if you want to have any kind of noticeable blink that's happening, you have to have it on for a while and then off for a while. and you're going to have to tell the Arduino to wait for a bit before going on. So now here's where you get another new function, delay. I'll put 500. So what delay is a function that says when the Arduino hits it, it pauses on this line for the specified amount of time before it continues on to the actual next step. What it accepts is milliseconds, is a number that you can put in there or a variable you pass in. And remember that 1000 milliseconds equals 1 second. So me putting here 500, I'm telling the Arduino to wait half a second. Now, this is very important to be later on, to be careful how you use delays, because again, it sits here and it'll do nothing else. In the real world, if sensor and information's coming in while this delayed, that information will be lost. It's like you closing your eyes and someone is waving at you and you're not going to see it until you open your eyes again. It's kind of like that delay. But for here right now, it means is when the code runs, it's going to come in here, it's going to go for high, it's going to delay for half a second, and then go low. But there's another problem in this code. I'll pre-warn you, give you a second to think, and then we'll go into the simulator and actually start running it. And you're like, well, look, it's not blinking, it's not changing anything different. Well, you got to remember that even though we have the delay, like we have the high, we have the delay before it goes low, is that, well, once it's done this last line of code, the loop goes there to the top of this and starts running all this code again. So we'll have high, a delay of half a second, but then we go low and then it automatically goes back to high. So you won't even really notice this. So you need another delay thrown in here. Boom. So the idea is so it'll be high, the light will stay on for half a second, then we send a low along the pin, basically telling the controller to stop sending power down pin 8, and then we do a delay for another half a second, and then it'll go back up to high. So let's start it now. Yay! 42 minutes, and we get to that whole thing where in university doing robotics, and we've made a light blink. Now, when I did this the first time, I think this kind of stuff is cool, but we'll see what other people think. So there you go. You got a light delaying and that kind of blink here. And so remember, these delays are going to be important if you want to visually see stuff or things you're doing when you're translating between how fast the machine is running to physically someone working with it. So if you want to change how fast it delays, you can start changing the delay that you see here in between. So higher numbers will make it be on and off, kind of blink slower, and lower numbers will make it blink faster because you have fewer milliseconds that you're working on. So if we change them both to 100, start simulation. There you go. Woo, disco lights. Not as much here. So again, the idea, that was dumb of me, is that, well, we have our one circuit. We can now, the Arduino allows for multiple circuits to be connected to this. You have your ground that's coming back to complete it, and we have this one individual circuit for just controlling this LED. We can have another LED thrown in here if we want to do other work and start doing work with two LEDs and building stuff up. We build another circuit, we hook ground to it, but then instead for the start of the power, we have another pin to it to control it along those lines. Okay, I think that's enough for the beginning of the simulator. You can next now move on to the physical device to see some of the differences you have there, where I'll show some of this same circuit and maybe play around with it a little bit more, and probably a shorter video because this video did more to explain the language, and the next video is going to show you more, okay, all the steps of getting the compiler, like the IDE installed, working with it, visually seeing what's happening, and hooking up the circuit again. Boop, boop, boop. Done.